So we're going to go over sample proportions today and how we deal with those, how we build confidence intervals for the true population proportion. So last class, I kind of introduced this idea. So just kind of a reminder, we're building confidence intervals, right? So we can build a confidence interval at different levels. So the typical levels we've been using are 90, 95, and 99%, which correspond to the alphas of 0.1, 0.05, and 0.01. Okay? We kind of had this set up, we ended last class with, which is we can really do a similar thing that we were doing with sample means, but do it with the sample proportion. So where this was coming from, let's switch over the dot cam here real quick. I always say real quick and I feel like I'm lying. All right, there we go. Zoom out a little. Okay. So with that sample mean, when we built our confidence intervals, it looks something like this, right? And then we knew that the standard deviation of our sample means was the original variance, or square root of the original variance over our sample size. So the sample proportion is the exact same thing. We're just using the standard deviation of our sample proportions, which we ended last class with. This would be the equation that we need to calculate that. Okay. So we can calculate this first and then plug it in, or we can plug that in right away and do it all at one time. Either way is going to work for us, right? But this is going to be the equation that gives us that confidence interval for sample proportions, because it's really the same thing we were doing before. Because remember, we said the sample proportion is just a unique version of the sample mean, where we're looking at the mean essentially of a 1-0 variable, right? So that's going to be the equation that we're using for our confidence interval. We're still using that standard normal distribution, right? So we're okay with, that's okay. So let's go here and look through an example, put some actual numbers to this, okay? So also, now I'm going to be correctly kind of referring to this as my margin of error. I said I always call what we add and subtract to our sample statistic the margin of error. Technically, that's the term when we're looking at proportions. I've been using it for sample means as well. It really just makes it easier to talk about this equation. So similar to the sample mean, we'll be kind of referencing what we're adding and subtracting to our sample proportion as our margin of error. Okay? So let's say we're looking at some survey data, and we see that in 2012, 63 out of these 81 people who were surveyed were in favor of covering health or insurance covering people that have pre-existing conditions. Okay, so yeah, oh, sorry, thank you. Don't just raise your hand, can you yell at me next time? So I'm switching the screen over in class here. Okay, right, so we were kind of saying, here's our margin of error, right? It's kind of similar to what we're doing with the sample mean. And here was our setup, right? So we had this survey, 63 out of 81 people. We're trying to build a 99% confidence interval. So 99% confidence interval, our alpha value should be what? Alpha is the area outside our interval, but in decimal form, yep, 0.01, right? 1% would be outside the interval, decimal form is 0.01. So what we're gonna do is identify the pieces of information we need. We had a sample size of 81. Our alpha we just said was 0.01. Alpha is going to help us find the z-score, sample size. So the only thing I need is my sample proportion. Well, I wasn't directly given that, but I was told that 63 out of 81 people, right, responded that they were in favor. So 63 out of 81, that's my sample proportion. So sometimes I won't directly be told, you find the sample proportion is, 0.63. Well, no, we were told 63 people out of 81. So we can calculate that sample proportion for ourselves. So what this simplifies to 7/9, right? Or approximately what, 0.777 repeated. I'll kind of just use the fraction to reference it since that makes it a little bit easier. So from here, it's really just a matter of plugging everything in. Right? I could do the intermediate calculation first. So it's going to be the square root of what? 7/9 times 1 minus 7/9 divided by that sample size of 81. I'm just plugging in my values there. And now that I have this, and I have my sample proportion, the only thing left I need to find is that z-score. So how do I find that z-score? Well, if we think about what we're looking for is what z-value is going to give us alpha total in the tails, which means that there would be alpha over 2 in each tail, or 0.01 over 2 is 0.005. Okay? So I want to look up that value of 0.005 and figure out what that z-score is. Okay, so and I'll leave this up here if you're still in this. A little small, but at least it's still there for a second. So we go to our tables. Oop, wrong table. Here's our z table. Oh, reopen that, apparently. Okay, so we go to our z table. Oh, maybe that's why it shut down on me. We're having some technical issues in class here. Give us 1 second. I think this hopefully will. There we go. Okay, so we've got our z table. We want that area of 0.005. So we start looking here, 0.002, 0.004. Looks like we're in between these two values. Right? So we go over negative 2.57, negative 2.58. So we'll take the higher in absolute value of the two, kind of that negative 2.58. We said the positive and negative really are built into our confidence interval equation. So we'll just put in the value of 2.58 up here. So now we have everything we need. What that will look like is, so 0.778 if we round it, right? We plug everything in. We can calculate that intermediate value. It's approximately 0.046. Now it's a matter of plugging everything into our equation, and we get this confidence interval with our lower and our upper bound, right? Subtracting that margin of error to get our lower bound, adding that margin of error to get our upper bound, okay? Any questions over that? Clarification on anything? Yeah.
Oh, never mind.
Okay.
Yeah.
Yeah, it just ends up being what that fraction is, right? I could have written in 7/9 here and would have worked as well. Okay. Now, what this is telling us basically is like with 99% confidence based off this survey, I could say that the true population proportion of people in favor of this is somewhere between what, 2/3 and 90%, right? So this is pretty strong evidence that, you know, if I'm trying to pass, you know, push this policy through, this is going to be pretty well received by the majority of the population. Because the true population proportion, I'm saying, is within this range of values with 99% confidence. And these are pretty high values, right? For 2/3 of people to be in support of something, that's pretty unlikely, or pretty rare. Okay. So let's go through one more example. So let's say, so this was actually, I'm trying to think which one I want to use. I've got a couple examples and we don't need to go through all of them. So I think I will, well, I'll go through this one because I think it's a little bit, there's a point in it that the other one doesn't have. So if we have this survey of 912 people and they were all registered voters, this was before the 2016 election. I actually kind of did some of this to try to kind of predict what was going to happen, right? So 46% of people from this survey said they were going to vote for Clinton. So if I wanted to build a 90% confidence interval for the true proportion of people who are going to vote for Clinton prior to the election, I could have done that, right? So what's my alpha value here? At 90% confidence, alpha would be, so alpha is the percent outside my interval in decimal form. So 10% is outside the interval, 0.1, my alpha, okay? So we got an alpha of 0.1. my sample proportion, if 56% of people responded they were going to vote for Clinton, the proportion of people who are going to vote for Clinton would be 0.46. Okay. And then I have my sample size of 912. Okay. So what I'm doing here, if I kind of keep track of this example, is I've got a pretty big survey now, right? Sample size is 912. Okay. Sample proportion was 0.46, and the alpha was 0.1 for the 90% confidence interval. So usually the first step that we would do is think about, okay, what Z value is going to give me that area of alpha total in these tails, or alpha over 2 in each tail. 0.1 over 2 is 0.05. Okay? So I'll go to my table. I know the area I want in the tail is 0.05. So hopefully it doesn't shut down on us here again. So I want 0.05 in the tail, so I'm going to look that value up in the middle, right? Because the Z-scores are what the column and row headings are. If I know the area in the tail, that's the values in the middle of this table. Right? So I start looking 0.04, 0.05. Looks like I'm in between these two values. Okay? So negative 1.64 and negative 1.65. So I'll take the greater in absolute value of those two, and I can kind of think about these Z-scores that would be negative 1.65 or positive 1.65. Now those signs are already built into my confidence interval equation, so really at this point I have everything that I need, right? So if I think about the general kind of form, and like I said, I always like to calculate the intermediate value. So what's the standard deviation of my sample proportions here? It's just the square root of, come back here, right? Sample proportion times 1 minus that divided by my sample size. So all I'm going to do here is plug my values in. So 0.46 times 1 minus 0.46 divided by 912. Okay. Now notice, when I have a sample size that's this large, what's going to happen to the standard deviation of my sample proportions? It's going to be pretty, the denominator is really large, what happens to the entire fraction? It goes down, right? It gets really small. At 912, dividing anything by 912, it's going to make it pretty small. Okay? So even though I'm going 1.65 standard deviations to the left and the right, well, if I'm going, let's say I wanted to go 5 standard deviations. Well, if the standard deviation is only 0.0005, well, that's not going very far, right? So we're probably going to be able to, with a sample size this large, we can probably get a pretty small margin of error and build a pretty tight confidence interval. Now, from this point, it's really just a matter of plugging values in. I got my 1.65, whatever this turns, I think this is like 0.016 something. Plug that in. We've got our 0.46. Plug that in. And that's just a little, pretty basic computation if we first calculate that intermediate kind of value, which is the standard deviation of our sample proportions. Any questions on that before we keep moving? All right. So, also I had this because I wanted to mention, hopefully at this point, we've seen this value of 1.65 pop up quite a bit, and we've seen 1.96 pop up. And the reason is because these are going to be some, kind of correspond to a lot of our benchmark values we want to look at, right? The area in between each one, oh, I have a small typo here. There we go. Right? These are kind of 80%, 90, 95, 98, 99, right? These are going to be some values that pop up a lot, just because these are some interesting benchmark values that we'll be using for a lot of different examples, right? So along with this same idea, right, we could go through and calculate everything. So yeah, it was 0.0165 was that standard deviation of my sample proportions. Now I have everything I need to plug those values in, and I get this confidence interval with a lower bound of 0.43 and upper bound of about 0.49. So what this is going to look like is something like this. So we could actually think about like plotting this if I move my, there we go. So 0.4328 what, 0.4872. So this is going to be thinking about the true population proportion of people who are going to vote for Clinton is somewhere in this range, right? I don't know where it is, but it's somewhere in there with 90% confidence. Okay? So what we could then do is look at that same survey and say, okay, 912 people responded to this survey and 40% plan to vote for Trump. So now I've got a sample proportion for the people who are going to vote for Trump, which is 0.4. If I build a 90% confidence interval for the true proportion, I can use this sample proportion of 0.4, my sample size, which is still, what, 912? And then I can use that same z value because I'm still looking at the 90% confidence interval. So anytime I want a 90% confidence interval, what's the area outside the interval in decimal form, or what is alpha? 0.1. I want half of alpha in each tail, so I divide it by 2, 0.05. I look 0.05 up in the table, I'm always going to find 1.6 or negative 1.65. Right? So I'll be able to use the same z-score, and I could then compute the lower and upper bound for Trump. Right? So this is just a little bit of, we could, it's kind of the exact same thing we did with a slightly different number. Right? Our only thing that's really changed is our sample proportion. Sample size was the same, and the z-score will be the same. So if I do that, I get 0.372. And here's where I should have had some foresight, right? So 0.3732 and 0.4267, okay? So I'm just kind of plotting those points, right? And here's what I want to make the, bring this idea up. So notice, if this is the range for which the true proportion of people who are going to vote for Trump is, at the 90% level, what can I say? Well, the upper bound for Trump is lower than the lower bound for Clinton. So here at 90% confidence, because these confidence intervals don't overlap for these two proportions, I could say that the population proportion of people who are going to vote for Trump is going to be less than those who vote for Clinton, right? Because this is the range with 90% confidence where I'm saying the true population proportion is. So even if the population proportion of people who are going to vote for Trump is exactly equal to the upper bound, and the proportion of people who vote for Clinton is exactly equal to the lower bound, this value would still be higher, right? So with 90% confidence, I could have said, based off the confidence intervals, that Clinton is going to end up with a higher percent or higher proportion of the popular vote, which sure enough is actually what ended up happening, okay? Now, we had a pretty big survey here, so it allowed us to kind of narrow these ranges of the confidence intervals down. What would have happened, though, if I wanted to say, okay, yeah, I can say this with 90% confidence, but can I say this with 99%? So if I want to say something with 99% confidence, well, before what we were doing was we had what? At 90% confidence, here was our z-score that gave us half of alpha kind of in each tail, right? So if I want to say something with a higher level of confidence, maybe 99% confidence, what's the area in what's my alpha? 0.01. So half of alpha in the tail would be what? 0.01 over 2, so 0.005. So if I want a smaller area in the tail, the only way I can get that is if I choose a higher z-score, right? So I don't know, I think we looked it up earlier, right? It's like 2.58. So with that higher z-score, right, is going to increase my margin of error, making my confidence interval wider, right? So if I want to say this with 99% confidence, what's going to happen is, well, my lower bound for Clinton and the upper bound get wider, and the lower and upper bound for Trump. And it's likely that they were already pretty close together to begin with. It's likely that they now overlap. So if they overlap, what's the issue? Well, let's say we'll keep using red for Trump, and actually, let me see, can really get this to match up here. And I can use blue for Clinton, right? So let's say at the 99% level, these intervals get wide enough to where they now overlap, right? Because they were pretty close before, right? There was early, 0.4267 is not very far below 0.4328. So at the 99% confidence level, it's likely they overlap. Why is this an issue? Well, because the population proportion of people who are going to vote for Clinton could be here, and the population proportion of people who vote for Trump could be there. So Trump would have a higher proportion, right? But it could be that Trump, the proportion was actually down here, and the true population proportion of people going to vote for Clinton was up here. Well, now Clinton is larger, right? So anytime they overlap, I can't really make any statements. With 99% confidence here, I can't really say whether or not the proportion of people going to vote for Trump is greater or less than Clinton, because any value in these ranges are potential value, true values for that population proportion. Okay? So we can start to use confidence intervals to make these statements. If they overlap, we're kind of out of luck, right? But in a situation where, like we had at the 90% level, where they didn't overlap, well, then we could actually say, well, with 90% confidence, the proportion of people who are going to vote for Trump is going to be less than those who vote for Clinton. Okay? Any questions on that before we keep moving? Okay. So we could do this for so one interesting thing about this was, just to be fully transparent, I was using this to try to predict it, and I thought it was an interesting example. Oh, here it is. This survey was actually from Fox News, so I tried to get like the most biased kind of towards Trump here, so we could get this example, or get the situation where the prediction was like that we don't know, right? But even at the 90% level, even with maybe the most biased survey maybe I could find, that there was still no overlap in those confidence intervals. We could have done a very similar thing for this last election, right? So I was looking at some of the data that was out there from the last election, and you could do the exact same thing for the proportion of people who are going to vote for Biden versus Trump. It just wasn't very interesting. So I built all these slides and then wanted to use this example. And then I realized when I compute this lower and upper bound, 0.51 to 0.56, when I looked at the same one for Trump, it was just so much lower. I couldn't really bring this point up of, well, what happens if we want to do 99% confidence? Would they overlap? Because here, right, they're pretty far away. That lower bound for Biden was pretty far away from that upper bound for Trump. So this one wasn't as good of an example, but it kind of highlights you could make these predictions for any kind of race for election or for any candidates to try to predict who's going to win, right? And basically by building these confidence intervals. Okay. Like I said, if you want to walk through these slides on your own, it might be some good additional practice just to make sure you can reproduce these numbers. But it's really just another example with kind of same sort of setup, but just slightly different numbers. This one's not as interesting, though. We notice those confidence intervals aren't even close to overlapping. Okay? And sure enough, the popular vote was a pretty big gap if we're looking at kind of what actually happened. Now, these were just surveys. So, and I think I had another one in there that had, was the one I could find that was closest, right? Based off their survey, we thought the election might be the closest, right? So here we have 51% and 47. And now when I built these confidence intervals, notice the lower bound for Biden was just barely below the upper bound for Trump. So we did have some overlap based off of this survey. However, right, there wasn't very much, right? But, with this survey, we could have said, well, we can't really say that Biden's going to end up with more of the popular vote based off of this survey, right? Because there was overlap in those confidence intervals, right? The upper bound for Trump would have been past that lower bound for Biden here. Okay? Any questions on that? Like I said, this is just some additional, might be good to kind of work through these just to make sure you get used to entering these into your calculator and being able to reproduce these numbers. Also, just kind of one thing that's interesting, you might see a lot of the times, like when they are putting these election predictions up, they'll tell you like what the survey said. So 47% of people are going to vote for Trump. And then they usually tell you with a margin of error of 3%. So that margin of error of 3% they're essentially telling you this, right? They're giving you the margin of error. Based off that margin of error, if you wanted to, when you see this like report in the news, it's pretty easy to construct a confidence interval, because if they give you the sample proportion and then they're telling you the margin of error, they already did the hard work for you. They found the z-score, right? And they calculated that standard deviation of your sample proportions, right? And if you had the margin of error, all you have to do is add and subtract that to the sample proportion, and you could build these confidence intervals. Okay. Any other questions before we keep moving? So what I want to make sure we get through today is, let's go back, and we're section 4. So we're going to look at this confidence intervals example file. And this is the one that we left off kind of working on. So we had that known SD and proportion where we're looking at school enrollment data, right? The number of undergraduates. So I'm going to delete this and kind of rebuild it and show you it's very similar to what we were doing before. Okay? So I have all this data of universities under enrollment, and I then created this variable which was a 1 if the total undergraduates were greater than 10,000, and a 0 if they weren't. So I have this binary variable, right? It's either a 1 or a 0. If I wanted to find the proportion of schools that, or proportion of universities that have more than 10,000 undergraduates, right? I can find that by simply using the average formula or finding the mean, right? We said a sample proportion is really just the mean of a 1-0 variable, okay? Because what the mean will do is it'll add up all the numbers. Well, if I add all these values up, the zeros don't do anything. So my numerator would be just the number of ones I have here, or the number of schools that have more than 10,000 students. And then it would divide it by the total number of observations. Well, that's just like we were doing there, like 63 out of 81, 1,000 out of 1,500, right? So that mean of a 1-0 variable gives me my kind of sample proportion. I have mean proportion here, but all right, we can think about it as our sample proportion. I can then find my sample size by using that count formula function in Excel. So I now have my sample size. We can think of this, right, as n. Got my sample proportion. The only other thing I need, right, is to find my z value. And then I could, oh, where is it? I had it on one of these things, right? And I could find the intermediate value of the standard deviation of my sample proportions as well. So I've got the equation right here for that. So if I think about standard deviation of my sample proportions, right, that's going to be the square root, so SQRT in Excel, that does our square root, of my sample proportion, which I have right here, times 1 minus my sample proportion, divided by, and my sample size, I can't click on this cell because it makes this box big for some reason, so Q2. I need to spend some time one day to try to figure out how I can reduce that. I know there's a way. So all I did was kind of use Excel to be my calculator and calculate this intermediate value, which is the standard deviation of my sample proportions. Okay? It's going to be mad because I didn't close the parenthesis. So now the only thing left is to find that z-score. So how did we do that? Well, it's going to be the exact same thing we did for sample means. I know the area I want in the tail is alpha over 2. So if I know the area and I want to find the z-score that gives me that area or that probability in the tail, I'm working in reverse or backwards or inverse. So norm.s, because I'm looking at the standard normal distribution for a z-score, a z-value. And then I'm working in reverse, so I and v, right? I know the area in the tail that I want is alpha divided by 2. Okay. Now what issue is going to occur if I simply leave it at that? Remember last class we said, oh, well, it's always going to give me the negative z value, right? Because alpha over 2 is going to be a kind of small value, small area in the left tail is going to be a negative z value. So we said there was 2 ways to fix this. We could do 1 minus alpha over 2, or probably the easier way, I think, is just take the absolute value, right? We just want the absolute value of that z-score because the positive and negative are already going to be built into when we calculate the lower and upper bound. Then I can just copy this down because my cell reference will update to the new alpha, so I can get the z-scores I need to build my 90, 95, and 99% confidence interval. Remember, they kind of corresponded to these levels of confidence over here. Well, notice these are the exact same z-scores I found when I was building confidence intervals for the sample mean on Wednesday. Now from this point, it's pretty easy, right? I think about, here's my equation for the upper and lower bound. So I'll take my sample proportion. For my lower bound, I'll subtract that z-score times that standard deviation of my sample proportion. Now, we talked last class. I could have, instead of calculating this first, put the equation in to this cell as well and did it all at one time, and I didn't even have to calculate the z-value in a different cell. I could have put the norm.s.i and v function in here all in one cell. It's just a little bit hard to see if you make a mistake, like or where things are going wrong, right? Kind of trace down. And also, honestly, it's good practice because we're going to be using these formulas for a lot of other stuff. So it's kind of good to just make sure you're seeing what the output is, right? Any questions before I keep going up to this point? Okay. So if I want to copy this down, what's going to be the problem? That doesn't look right. I'm looking at a sample proportion that should be between 0 and 1, right? Oh, yeah, I did want the z-value to update, but I didn't want these to start moving, right? So I go back, okay, I don't want the sample proportion to ever change, right? No matter if I'm building a 90, 95, or 99% confidence interval, that sample proportion, I'm building my confidence interval around it, right? So I don't want that to ever change as I copy this down. And that standard deviation of my sample proportion, well, that won't change either. The only thing that's impacted by looking at different levels of confidence is that z-value, or the number of standard deviations away from our sample mean that we're going to go. So I'll freeze that standard deviation of my sample means, and the only thing I'm not freezing is that z-value, so that when I copy it down, well, now it keeps building the confidence interval around the same sample proportion, but it's using that new number of standard deviations away we need to go, or that new z-value. So then, how do we get our upper bound? Well, it's going to be the exact same equation. So I said the easiest way to do this, double click, you can see the formula, copy to get out of the cell. If I hit enter, right? Then double click over here, and we can paste that. So now when I copy paste like that, none of the cell references, change. And then instead of subtracting to get my lower bound, I add to get my margin of error to get my upper bound. Simple as that. Now I can copy this down, and I've got my lower and upper bounds for 3 different confidence levels. Now, you'll notice when I want to start saying things with higher levels of confidence, right? So higher levels of confidence means smaller alpha values. It should be that my confidence interval is getting wider, right? I'm getting a higher z-value, so that should widen my confidence interval. Sure enough, my lower bound is getting lower, and my upper bound is getting higher. Any questions on this? So I also wanted to mention, now, what I'm going to do here, you can't just do this, but I'm doing it to make a point. Let's say instead of 111 that's my sample size, let's say I had like 500. What should happen to my confidence intervals here? The sample size goes up. So if my sample size goes up, that standard deviation, right, if the denominator is larger, the standard deviation will go down. So then when I multiply that z-value by the standard, I have a smaller margin of error, which means I'll have a kind of more narrow or a smaller confidence interval. If it's not easier for you, so for me, it's easy to remember, like I remember this mathematically because I think about these equations and I think about, well, if n goes up, I've got a larger denominator, it's going to reduce it, it's going to make my margin of error smaller. So that is the mechanism. If it's easier, just think, if I have more observations, I have more information about the population, right? So I should be able to get a more accurate idea of where the population mean is at. What is a more accurate idea? Just a more narrow confidence interval. So having more information, this larger sample size, I can get this much more narrow range or a better idea of where that true population proportion or population mean is. So sure enough, if I change this sample size, decrease my standard deviation of sample proportions, and just to kind of remember, so 0.73 to 0.85, 0.75 now to 0.8, just under 8.3, right? So, or actually 0.82. So, right, it did reduce it, maybe not as much as maybe you would have think, you know, but it does make that interval smaller. Okay. Any questions on this? Anything that we kind of just did in Excel? So it's really, I mean, everything we did Wednesday for sample means, it's very similar for our sample proportions. It's just that we're finding the mean of a 1-0 variable, and our standard deviation equation is a little bit different. Okay. I wanted to say something else, and now I think it escaped me. Oh, so this file, right, this confidence interval example, and I'll post so I'll keep the original one up there, but we've done some additional stuff that I was just showing you different things. I'll post this one up there and call it something else like confidence interval example in class work, right? So if you do want to reference anything that we've done in class, you'll have this sheet, but I'll also leave up the original file. That doesn't have quite as much because, right, you don't need to build the confidence intervals twice, right? For if I asked you on a homework, I was just showing you there are two different ways, or there are different ways of doing this. So this will be a really good template for that assignment, and I'll get that posted after class today. So you'll be able to get through, there's kind of like 3 questions, but yeah, so you'll be able to get through questions 1 and 2, right? I can't remember now if it's 3 or 4 questions. I might have broken it down to part A and B, or maybe I created 4, but you'll be able to get through about 2/3 to 3/4 of the assignment based off of what we've done to this point. It's a lot of building confidence intervals. It's a lot of getting used to using that norm.dist and norm.s, or sorry, norm.dist, norm.inv, norm.s.dist, like we did with the Indiana weather data. So that's kind of the first part. So you'll be able to get pretty far through it. It won't be due for another 2 weeks, so 2 weeks from Friday. Because next week, what we're going to do is cover situations where we don't know that population variance. So all these examples should seem a little weird, right? When we talked about the proportion, we said, well, technically, if I go back here enough, technically, when we calculate the standard deviation of our sample proportions, we should be using the population portion. But we don't have that, right? That's the whole reason we're building confidence intervals, so we had to estimate what that was. Well, in all these sample mean examples, right, I was using the population variance, but I didn't know what the population mean was. How did that happen? Well, usually it was because we had some production process, so maybe we know the variance of the machinery, but more often than not, we don't know what that population variance is, and that's going to present some problems. Right? Now, similar to the proportion, we basically just use our sample variance as the best estimate for what the population variance is. Right? We look at our sample, calculate the variance, okay, well, that's the best guess we have about what the population variance is, so we'll use that. Now, the problem is, when I calculate that sample variance, we go all the way back to like week 1 or week 2, right? You know, n-1, right, is going to be in the denominator of our sample variance, right, kind of hiding behind the scenes. Well, the problem is, if I'm using this as an estimate about where the population variance is, if I divide by 1 instead of 2, right, let's say n was 2, dividing by 1, n-1, 1 instead of 2, that's going to create a big difference. But if I divide by 99 instead of 100, right, take sample size of 100 minus 1 is 99, that's not going to cause that much of a difference between that sample variance and maybe what the true population variance is. So the fact that we're using n-1 here to calculate the sample is going to make the standard deviation of my sample means a little bit off. Right? So, you know, notice here, this is still, even though the notation is a little different, this is still the standard deviation of my sample mean distribution. It's just when I write this as an S, that indicates I'm using a sample variance to calculate it as opposed to the true population variance. But other than that, things are going to be pretty similar in the way we proceed when we're trying to build confidence intervals for sample means or where the true population mean is. Okay? It's just we're going to use our sample variance as the estimate for what the population variance is. Now, the procedure is the same, but there's one problem, right? So before, when we were looking at sample means, we had the confidence interval equations that looked like this. Right. Now, what's going to be true is, well, we have to write this a little bit differently because we're calculating the standard deviation of our sample means using a sample variance, whereas before, we were using that population variance. And because there's this issue, this n-1, if I were to try to convert these sample mean values into z-scores, what ends up being true is if I just subtract the mean and divide by this standard deviation, I actually wouldn't end up with a standard normal distribution. It's going to be a little bit off because the standard deviation I'm dividing by is using this sample variance where I'm dividing by n-1. So we're going to have to use a different distribution. We still want to find how many standard deviations away we need to go to get alpha over 2 in the tail. The issue is we're not going to be able to use kind of this standard normal distribution. We're going to have to use these student t distributions. Okay? So I say distributions because for every single sample size, we're going to be a little bit off from that standard normal distribution, right? When my sample sizes are really low, I said dividing by n-1 is going to create a much bigger issue than when my sample sizes are large. So for every single sample size, I'm going to have a distribution when I subtract the mean and divide by the standard deviation that's going to be a little bit off from the standard normal. It'll still have a mean of 0, but the variance is going to end up being a little bit higher, right? Which kind of makes sense. If we're dividing by n-1, right, or instead of n, it's going to make it a little bit higher, right? A little smaller denominator makes the value higher. So we end up with every sample size is going to have its own student t distribution. Okay? So what does that look like? Oh. So I said the variance is going to be a little bit higher. So the other idea there is it's a little bit more spread out, right? Its variance isn't equal to 1. It's really close to the standard normal distribution, but the variance is going to be greater than 1. Right? It'll still have a mean of 0. And we're going to start calculating these things called the degrees of freedom. I'll go a little bit more in depth probably once we get to hypothesis testing about what this degrees of freedom is. But for now, just know that it identifies which student t distribution you should be using. Okay? So I already mentioned that mean is 0, but I didn't mention it's also symmetric, just like the standard normal distribution. So that makes things a little bit easier for us once we start working with it. But it's a little bit more spread out, right? So the variance is going to be higher. So if the variance is higher, right, as we get this higher and higher sample size, the variance starts to get closer and closer to 1. If it could ever get to 1, basically that would be a standard normal distribution, right? Mean 0, variance of 1, symmetric. That's our standard normal distribution. Now, it never truly gets to there because for a student t distribution to converge to a standard normal, theoretically what we would actually need is an infinite number of degrees of freedom. Well, we can't have an infinite sample size, right? So, once we get past 100 though, it's so close, like the variance is going to be so close to 1 that we could actually just use a standard normal distribution to approximate it. Okay? So with this in mind, I think I'll probably save, I think we're running a little on time, so I'll save this for kind of early next week. But I do want to just show you the table real quick. So I'll get this up on, oh, come on. Let's try this again. Maybe I'll show it to you. There we go. So it's going to be a little bit different than our standard normal table. instead of looking at the area to the left, it only shows us positive values. So we're only thinking about the area to the right, okay, in that upper right tail. Now, the row headings will be your degrees of freedom. So once you take your sample size, maybe say your sample size is 30, you subtract 1, you get a degrees of freedom of 29. This should be the row that you're looking at. Okay? Now, in the middle of the table, these are going to be t-values, and they'll be the t-values that give you this area in the upper right tail. Okay? So the idea would be if I wanted let's say, we were building a confidence interval and I wanted half of alpha in each tail. So maybe half of alpha ends up being 0.025. If my degrees of freedom was 29 and I wanted 0.025 in the tail, the t-value that would give me that is 2.04. Right? So we're still using it to find these values for our confidence interval, right? These t-values now instead of z-values. It's just that it's almost like the opposite of the z-table because the area in the tail is now our column heading and our values are in the middle. Whereas with a standard normal table, right, we're using the kind of row and column headings for our z-value, and then the probabilities of the area in the tail was in the middle. So it's kind of flip-flopped. Right? Now, obviously we only have, 6 different areas in the tail here, so we're going to be somewhat limited. So eventually we're going to get to a point where we say, look, we can use this table, but really when we're dealing with a student T, it's a lot easier to probably do some things in Excel as well. Right? But for confidence intervals, this table will be pretty nice. Okay. I think I'll leave it there. I just want to kind of introduce you to the student T distribution. We'll talk a little bit more in depth about it on Monday, and then start working through some examples by hand and also in Excel, and then we should have everything you need to kind of complete that Excel assignment after class on Monday. Okay. I also want to mention this isn't 100% sure yet, but I'm gonna guess that we won't have class. We won't have class next Friday. Okay. So if that's the case, I might put up an additional video that day. But there's a pretty high chance that I will end up canceling class on Friday. I'm just letting you know in advance. It's not 100% yet, but probably is going to happen. Okay. All right. I will see you guys on